check. Hello, can you guys hear me online? Okay, all right. Sure. Yeah. Sorry for the delay, guys. I think that there was something else going on in this room, and now everything is fine. Let's quickly get started. There's also, just to tell you, today's lecture might get over a little early. I have a lecture in Dadar at 6:30. So let's see, maybe instead of 6, we can maybe stop at 5:50 or something like that. Okay. Well, let's try to make up for all the lost time. Let's continue. In the previous class, we were seeing angular collisions. And if you remember, we covered this type of case where you have collision between a rod which is hinged, okay, and a particle. And we saw what happens when there is inelastic collision and what happens when there is elastic or any other type of collision. And we said that the concept you can apply is you can not apply conservation of linear momentum because of a hinge reaction, but you can apply conservation of angular momentum about the hinge. So that's one equation. And then if it's not an inelastic collision, you also have the coefficient of restitution equation. Similar to this is also if pure rolling body which is going to undergo pure rolling na, uske saath bhi agar collision hoga, right? So in that case as well, yahan pe you will have friction, right? Pure rolling ki case mein bhi you will have friction. So because of the friction, again, if some particle comes and collides with this guy, you'll again treat it like a hinged rod question, where this is the IAR. This is ultimately the axis about which you'll conserve angular momentum. जैसा वहाँ पे hinge force गायब होगा, या hinge force का torque गायब होगा, वैसे यहाँ पे friction का torque गायब होगा. So it's going to be a similar approach. But now we see cases where, in fact, just make a note of this, that, you know, even pure rolling is, just make a note of that. Pure rolling is pure rolling objects. So collision with pure rolling objects is similar to type 1. Type 1 was hinged rod. It's similar to the hinged rod case. The lowest point behaves as the hinge. The lowest point behaves as the hinge. Okay. Yeah.
So we take IAR as the point of rotation, the axis of rotation, because then the torque from friction becomes zero. Right?
Yeah. I mean, yeah.
If we would have taken another point, then we have to consider torque.
Yeah. So just for the sake of others in the meeting, what he was asking was, why are we taking this axis? We are taking it because iske about torque zero hoga. जैसा हमने तभी हिंज के अबाउट एंगुलर मोमेंटम कंजर्व किया था क्योंकि हिंज के अबाउट टॉर्क 0 था. Same reason. This is just like a hinge for this body at this instant. Yeah, same. Cool. We'll now see type 2. Okay, so type 2 is where you have a rod which is free to move. Okay? Rod which is free to rotate. Free rod. Free. Just, yeah, still under angular collisions. Type 1 was a hinged rod. Type 2 is a rod which is free. Yeah, free on a horizontal smooth table.
So, in this case, could we conserve linear momentum?
Yes.
Because then there would be no normal force.
Very nice. So, Ariditya is saying ki, can we conserve linear momentum? Because in this case, there is no hinge. So hinge ke karan you'll not have any reaction, right? So yes, you can. That is going to be one of the equations. So rod which is free on a smooth table. Isko bhi approach karte waqt and divide it into two cases. Case A is, had I divided last time as well? Okay, fine. Perfect. So yeah, again, we look at it that way. So case A is when you have an inelastic collision. You'll find that this is just one level simpler because इसमें एक unknown और एक equation कम मिलेगा तुम्हें, ठीक है? So inelastic collision with a free rod, all right? So imagine that this is the scene before collision, okay? And imagine this. So before collision, imagine कि rod rest पे है, but let's say you have a particle of some mass. Let's say rod का mass m2 है, length l है, particle का mass m1 है, and particle is striking the rod with a velocity v. ठीक है? And let's say the particle is headed for a point which is x distance. Let's just say x distance below the center of the rod or the center of mass of the rod. Okay. So this is the scene before collision. And naturally you can have a scene where the rod is also rotating and rod is also moving. Okay. The scene after collision, but even if the rod is rotating, that does not really increase the amount of equations.
So there's no hinge here.
There's no hinge. It's a free rod. So it's like pen fight खेलते हो ना, कभी खेला टेबल पे पेन डाला है, पेन को स्ट्राइक किया है. So we're going to see that now based. Ha, perfect. So based on where you strike the pen, it would either, you know, so you can cause it to, if you strike it at exactly the center, you can cause the pen to move without rotating. If you strike it near the edge, you're going to find that it rotates a lot and maybe moves a little bit. Thoda between the middle and the edge, you'll find that it moves ahead as well, significantly, rotates as well, significantly, right? So that's exactly how a scene is going to look like after collision. So this rod now after collision will both move ahead, okay? And if you're not sure rod किस direction में जा रहा है, यहाँ पे तो आगे जाएगा, but even if the rod is moving towards the left, you don't break your head over which direction it will move in. Just assume a direction. If your assumption is right, अंत में पता चलेगा. नहीं भी अगर गलत है, negative आया, that just means you have to change the direction you've assumed. Okay, and then all is fine. So don't waste too much time. अब इस केस में
M1 would stick to the rod.
हाँ, so yes, M1 will stick to this rod. And इस केस में it seems pretty straightforward कि rod right की तरफ जाएगा. इस केस में rod कैसा घूमेगा, that also seems very straightforward. You've all played pen fight, so you know कि अच्छा ये particle ऐसा strike करेगा तो anti-clockwise घूमेगा. But again, my point is अगर obvious नहीं है, ठीक है, if there are two opposing motions, just pick one direction and figure out later whether that direction is correct. Don't waste too much time guessing the right direction. Okay, so that's it. So if you can see, this will completely summarize the motion of the objects after collision. Inelastic में एक फायदा ये है कि this particle is going to stick to the rod, so that's a good thing because
we'll have the same omega at the same
Yeah, it'll have the same, it'll basically move along with this point on the rod, right? So therefore, you'll have, you don't really need a new variable to describe the motion of the particle.
VCM and V would be equal.
VCM and
V.
नहीं यार, वो तो सवाल ही खत्म हो गया ना. VCM and V won't be equal, need not be equal. That's what this entire thing is about. We want to find VCM in terms of V. I hope you get a feeling कि ऐसा जरूरी नहीं है कि equal होना चाहिए. Right? Based on where you're going to hit, you're going to get different values of VCM. It can't this always be equal to V. All right. So in this case, if you can see over here, we have two unknowns. Right? So दो unknown है. Two unknowns. VCM and omega. So we need two equations. Okay? Very nice. Two unknowns, two equations. Okay. Maybe you can spill into this side. So two equations. So one is conservation of linear momentum. Obviously, there is no external force.
So,
and
there was no VCM in type 1.
No, there's no VCM in type 1. But even if there is, you will be able to. So as we'll see the equations, even if there is, you will be able to include that. It's not a big deal. Okay, the equations dekhte hain, and then you will understand kya karna hai. The two equations. The first equation is conservation of linear momentum. Okay. This is valid because there is no external force, no external impulsive force. Okay. So one thing to remember while applying this equation, चलो इस example में लिख ही लेते हैं equation. तो कैसा दिखेगा इस example में? M1V plus M2 into 0. Okay, very nice.
Is equal to M1 plus M2 the whole into VCM.
नहीं, ठीक है. तो इसमें like क्या हो गया ना? M1 का linear momentum लिखते वक्त you have to realize M1 का velocity VCM नहीं है.
The whole velocity. No, center of mass.
Rod का center का VCM है. So now you'll have to figure out कि यार इसका velocity क्या होगा. तो imagine this rod VCM velocity से आगे जा रहा है.
Omega.
Perfect. और rod घूम भी रहा है. तो रॉड के हिस्सा, एक तो रॉड के साथ साथ फर्स्ट टेक रोटेशन आउट ऑफ द पिक्चर, रॉड के साथ साथ ये VCM वेलोसिटी के साथ आगे जा रहा है, राइट?
So what's the speed of M1 after the collision?
That's what we're trying to write. Okay, so it's attached to this point on the rod. तो पहले देख, रॉड के साथ साथ VCM वेलोसिटी के साथ आगे जा रहा है, but then on top of that the rod is rotating, and because of that rotation, and especially this anti-clockwise rotation, can you see that relative to the center of mass, these points will have a backward velocity because ये ऐसा घूम रहा है, anti-clockwise घूम रहा है ना? And relative to the center of mass, these points, lower points, will have a forward velocity relative to the center of mass. तो एक तो center of mass के साथ साथ आगे जा रहा है, और फिर center of mass के relative ये और आगे जा रहा है. इनफैक्ट कितना आगे जा रहा है center of mass के relative?
But that's just for rotational वाला part.
हाँ, rotational वाला part कितना हो गया? R ओमेगा, है ना? सेंटर के अबाउट घूम रहा है, सेंटर के अबाउट घूम रहा है, सेंटर के से डिस्टेंस इसका x है, तो सेंटर के हिसाब से रोटेशन के कारण इसका वेलोसिटी हो जाएगा x ओमेगा. And that is on top of that you are also moving along with the center with velocity VCM. Right? So for this guy, both of these velocities add up, and उसका velocity हो जाएगा VCM plus x omega, right?
And it would have struck up at above, then it would have been negative.
हाँ, I mean in this instant, if I were to label, for instance, just for fun, इस point का velocity just like that, और इसका distance अगर y है, तो एक तो क्या होगा?
VCM minus y.
Perfect. तो सेंटर के साथ साथ VCM वेलोसिटी के साथ आगे जा रहा है, बट सेंटर की रिलेटिव ओमेगा का डायरेक्शन देख के बोलो कि और अब ओमेगा के वाई रेडियस इनटू ओमेगा माइनस वाई ओमेगा वेलोसिटी से पीछे जा रहा है बेस्ड ऑन द सेंस ऑफ द रोटेशन. सो इसका आगे की तरफ वेलोसिटी विल बी vcm माइनस y ओमेगा.
Doesn't that make a center of mass the hinge?
हाँ, any you can do this for any point on the rod. This is not center of mass का जादू.
But center of mass पे what become hinge?
हाँ, the reason we are taking the center of mass is because चलो center of mass का least complicated motion होता है, सीधा जाएगा. बट ये जो अभी अभी लिखा किसी भी पॉइंट के लिए लिख सकते हैं. तुम इसका पॉइंट वेलोसिटी v ले लो, तो बेस्ड ऑन ओमेगा सम पॉइंट l डिस्टेंस अबाउट इट विल बी v, मतलब इसके साथ साथ v बट इसके रिलेटिव l ओमेगा, तो v प्लस l ओमेगा. तो किसी के हिसाब से भी तुम लिख सकते हो. ठीक है, we're just right now working with the variables we have already assumed. Okay, so we are writing this way. So looking at that, m1 ka angular momentum becomes m1 ka linear momentum becomes m1 into vcm plus x omega. This is its linear momentum after the collision. Okay, what is the linear momentum of the rod m2? हाँ हाँ, तो रॉड का प्लीज ये ध्यान दो, दिस इज वेरी इंपॉर्टेंट कंसेप्ट दैट यू गाइस शुड नो. कोई भी एक्सटेंडेड बॉडी का लीनियर मोमेंटम इज इट्स मास टाइम्स द वेलोसिटी ऑफ द सेंटर ऑफ मास. ठीक है, कोई भी एक्सटेंडेड बॉडी का लीनियर मोमेंटम, दैट्स इट. डजंट मैटर वेदर इट्स गोइंग स्ट्रेट, वेदर इट्स रोटेटिंग, कुछ फर्क नहीं पड़ता है. लीनियर मोमेंटम इतना ही होता है, m2 into velocity of the center of mass. Okay.
Oh, but sir, shouldn't it be vcm plus x omega pt?
Linear momentum body का, rod का, ठीक है, any extended body का linear momentum is m times vcm. वो
center of mass पे x
वो defined. हाँ, center of mass का तो
because like it makes sense ऐसे कि like if the pen is rotating and moving, so then it will like have like higher momentum and then
नहीं, so it will have whatever you're perceiving as higher is not really linear momentum that you're perceiving as higher. ठीक है, and वो simple सा ये proof है यार. कोई भी system है ना, system के बहुत सारे particles है, तो पूरा system का linear momentum is summation of हर particle का linear momentum. और हर पार्टिकल का लीनियर, हाँ, तो mi vi ऐसा आ जाता है. एंड देन व्हाट डू यू नो अबाउट vcm का डेफिनेशन इज इन vcm summation mi vi अपॉन टोटल मास, राइट. तो वही से देख लो क्या आ गया. कोई भी बॉडी का लीनियर मोमेंटम रिजिड हो, इट मे बी गोइंग स्ट्रेट, मे बी रोटेटिंग, मे बी डूइंग एनीथिंग, कोई भी एक्सटेंडेड बॉडी का लीनियर मोमेंटम इज डिफाइंड दिस वे, टोटल मास टाइम्स vcm. Okay, we could have even like is final system का भी momentum लिखते वक्त instead of two terms we could have taken total mass m1 plus m2 and velocity of that system's center of mass, but it takes some time to figure that out, so we just wrote it this way. Okay, cool. हाँ, so here I'll just stress even as you're writing this, linear momentum always uses vcm. Remember that. Always uses velocity of the center of mass. Always uses velocity of the center of mass. Contrary to what we had seen for coefficient of restitution, that uses velocities of the points colliding. So that's equation number 1.
Yes, sir.
I wish there was a copy option. Yeah.
So on the bottom right corner, then of that square. I don't know what that does.
No. You can select it and then copy it. Selection options.
Yes, यही है selection window यही है. अरे never mind. ठीक है. अभी second equation. So for the second equation, we have conservation of angular momentum. Okay. किस एक्सिस के अबाउट एंगुलर मोमेंटम कंजर्व किया जा सकता है?
Center of mass.
इज दैट इट?
Yeah.
क्राइटेरिया क्या है कंजर्वेशन ऑफ एंगुलर मोमेंटम के लिए?
Torque should be
zero. Do you have torque about any axis? कोई भी एक्सिस के अबाउट टॉर्क है ही नहीं.
so we could take it.
So you can take any axis. तुम कोई भी एक्सिस जो चाहिए वो एक्सिस के अबाउट you can conserve angular momentum. Okay. So
it depends on the axis of rotation, right?
नहीं, it doesn't depend on the axis of rotation. Simple सा point है, angular momentum about any axis is rate of change of angular momentum about any axis, either random सा इधर एक fixed axis के about भी कर सकते हो, is torque. अगर कोई भी random सा axis के about torque zero आ रहा है, उस axis के about angular momentum will be conserved. Okay, that's it. That's the statement. So अब इस case में, because there is, ठीक है, no friction anywhere, there is really no torque. कोई भी axis में लूंगा, यहाँ पे body के center पे ले सकता हूँ, या इधर side में any fixed axis anywhere I can take. उन सारे axis के about तुम्हारा torque zero होगा, तो angular momentum will be conserved. Okay, so I'm just going to say that torque is zero about all axes, right?
We could take it at the point where we have one mass contact.
Excellent, excellent, very nice. So therefore Li equal to Lf is valid about all axes. ठीक है?
So, but here we are defining center of mass, okay, as the axis. Right?
नहीं यार, that's a कहाँ कौन सा axis? वो तू इधर अटका है क्या? मैंने इसका velocity center of mass use करके लिखा है, इसलिए बोल रहा है तू? That was just why have I used center of mass का velocity to write the velocity of this point? The only reason I did that because I have already assumed those variables. I didn't want to write a new variable. Why did I assume those variables? They're the most logical and the most important things that we would want to know. We would want to know the velocity of the center of the rod and we'd want to know omega. ठीक है? So इधर कुछ heavy concept नहीं लगाया. I again said what we did over here could have really been done using any other point. It's just I am using VCM and omega. I need to find that, so I'm writing everything in terms of that.
That's the same thing for angular momentum.
हाँ, so angular momentum भी हम VCM और omega के terms में ही लिखेंगे. We'll not keep adding new unknowns. Now the point over here is torque is zero about all axes. So angular momentum is valid about any axis you pick. Okay, that's a separate and completely valid concept. What this guy Aryaditya was saying is, he's saying कि यार M1, ठीक है? So M1 जहाँ पे इसको hit करने वाला है इस rod को, ठीक है? So you're saying that is a good axis to pick. Fair enough. And I hope the axis you have in mind is not a point on the rod जो rod के साथ साथ घूमेगा and will make things complicated. I hope the axis you had in mind was a point which is going to just stay where it is, right? So let me make it a little bit more clear. Maybe you can take any, you can take an axis over here, something along this line. And let's talk about why that will be a good choice. एक बार वो final scene भी वापस draw कर लेता हूँ. तो ये VCM है अपना, ये अपना omega है, इधर M1 चिटका हुआ है. I'm just drawing the same axis in the final scene as well. Okay, and we know इसका velocity ये सब तैयार है. This is VCM plus x omega. Okay, so over here I said Li equal to Lf is valid about all axes. It's up to you to choose an axis. Let's choose an axis which will make things simple for us, right? Which will make as many terms as possible, will make those terms 0. So according to me, the best choice of an axis is this one. Q.
Because the angular momentum of the particle becomes 0.
Very nice. Angular momentum of the particle becomes 0. Before वाले angular momentum में particle का गायब होगा.
So you're not choosing the axis on the rod because R will be 0, right? Like other rod will select the radius will be 0, right?
किसका radius?
So conservation of angular momentum. No,
Hmm.
I'm asking why are you
हाँ.
taking the axis on the rod?
Firstly, I don't want a moving axis. ठीक है? You want to conserve angular momentum as a useful equation. Just take a fixed point somewhere else. Don't take an axis which is moving along with the rod. Okay, that's going to make things complicated because then तुम्हें बैठ के relative velocity वगैरह सोचना पड़ेगा. So don't take a moving axis. Take a fixed axis. We know how to write angular momentum about a fixed axis. याद है वो formula ICM omega plus RCM cross MVCM. So we know how to do that. ठीक है, तो मैं एक fixed axis जो भी लूंगा एक बाहर लूंगा. Maybe your question is why is your question this? Why am I not taking an axis which is maybe next to the center of mass?
Yeah.
So I'm saying that will be the next best choice. That's also a valid option. That'll be the next best choice. यहाँ पे तुम एक axis ले सकते हो, center of mass वाले line पे यहाँ पे भी ले सकते हो. So these are this is your first best choice. This is your best choice. In my opinion, इसमें more often than not, you'll have comfort working with this. We'll try to write the equation, तब तुम्हें समझ में आएगा, है ना? क्यों क्या पार्टिकल का इनिशियल एंगुलर मोमेंटम भी गायब हो जाता है, पार्टिकल का फाइनल भी गायब हो जाता है. एंड फाइनल देखो वो गंदा सा VCM plus x omega, that गंदा सा टर्म जा रहा है. So this is definitely a good choice. Maybe this one could be your second best choice. इसमें भी फायदा है, like for instance इसमें VCM वाला टर्म गायब हो जाएगा. रॉड का एंगुलर मोमेंटम लिखते वक्त ना दो टर्म होता है, ICM ओमेगा प्लस RCM क्रॉस MVCM. इसमें रॉड का ट्रांसलेशनल वाला जो है VCM वाला टर्म एंगुलर मोमेंटम, that will disappear. But let's stick with I think the best choice. So is valid. So choose, I would say choose one of the highlighted axes. One of the highlighted axes. So let's try to write equation लिख लेते हैं इस example के हिसाब से. Let's try to write the equation for that angular momentum. So now before writing either linear momentum का equation या angular momentum conservation का equation, always choose a direction that you decide you consider as positive. जैसे collision में you always, I hope, एक डायरेक्शन पॉजिटिव अज्यूम करते हो ना बिफोर राइटिंग, वैसा ही एंगुलर मोमेंटम के लिए भी तुम्हें करना है. सो जस्ट चूज अ डायरेक्शन टू बी पॉजिटिव. तो क्या लेना है पॉजिटिव, एक बता दो, क्लॉकवाइज या एंटी क्लॉकवाइज? ठीक है, एंटी क्लॉकवाइज. ठीक है, डजंट मेक अ डिफरेंस, सो डोंट वेस्ट टू मच टाइम, जस्ट बी क्विक. एक डायरेक्शन पॉजिटिव अज्यूम करो, उसके हिसाब से अब सबका एंगुलर मोमेंटम लिखो. सो वी आर गोना से कि एल इनिशियल ऑफ द पार्टिकल, ठीक है, पार्टिकल को मैं शॉर्ट में P लिखने वाला हूं इसके आगे, प्लस एल इनिशियल ऑफ द रॉड इज इक्वल टू एल फाइनल ऑफ द पार्टिकल प्लस एल फाइनल ऑफ द रॉड. एल इनिशियल ऑफ द पार्टिकल क्या है अबाउट द बेस्ट चॉइस वाला एक्सिस? 0. ठीक है, सो आई एम जस्ट सेइंग दिस इज अबाउट about this black axis. So 0, very nice. क्यों? Because this particle passes through the axis. R perpendicular ही नहीं है, परपेंडिकुलर डिस्टेंस ही नहीं है, ठीक है। फिर रॉड का इस एग्जांपल में तो रॉड रोटेट ही नहीं कर रहा है, तो रॉड का एंगुलर मोमेंटम इज जीरो, ना ही रोटेट कर रहा है ना ही घूम रहा है। फाइनल एंगुलर मोमेंटम ऑफ द पार्टिकल is also zero. So this is why I picked this axis. Now, final angular momentum of the rod, you have two terms, ICM omega plus RCM cross MVCM.
So,
Ha.
angular momentum about the rotation of center of mass is equal to the angular momentum of the axis. But
Of-
opposite direction, so it becomes
हाँ, yes. So you're saying, हाँ, तो ये बोल रहा है कि यार यहाँ पे सब जीरो है, तो रॉड का जब हम लिखेंगे ना ICM ओमेगा प्लस RCM क्रॉस MVCM, तो बोल रहा है कि these two terms will cancel out because they're going to be in the opposite sense, and yes they will. This is, let's write that term for a rod. तो यहाँ पे सब कुछ जीरो हो गया. ICM ओमेगा, रॉड का ICM will be ml square by 12, right? अच्छा, ओमेगा डालते वक्त just bear in mind to look at the direction. अच्छा, ये एंटी क्लॉकवाइज है, तुम्हारा कन्वेंशन भी एंटी क्लॉकवाइज था, तो you will put this as positive omega. Next term RCM cross MVCM, ये याद करो, this was nothing but, चेक करते हैं, this was nothing but R perpendicular, है ना, बस R perpendicular सेंटर ऑफ मास से देखना है, which would be x. Very nice. So this is x, right? तो इसको extend कर लो, this distance is x, this is R perpendicular for this axis, right? तो R perpendicular आ गया x, so this term is x into mass of the body. I've not been writing the masses. ये rod है, तो m2, okay, m2. So m2 L square by 12 omega plus x m2 into velocity of the center mass. कितना easy है. अब बस ये देखो कि यार ये वाला जो term है about the axis, center of mass का motion, is it in the clockwise sense or the anti-clockwise sense? Axis इधर है. Just imagine completing the circle. So you'd have to rotate in the clockwise sense to further complete the circle. ठीक है, तो ये clockwise हो गया. Because ये clockwise हो गया, यहाँ पे minus sign आएगा.
Sir, क्या clockwise होता है?
Center of mass का motion above the axis. ये axis इधर है, center of mass ऊपर से pass कर रहा है. So if you complete the trip above the axis, तुम्हें clockwise घुमाना पड़ेगा. नीचे से pass कर रहा था तो anti clockwise. ऊपर से right की तरफ जा रहा है तो clockwise, है ना? Okay. So जिस ब्रैकेट में डाल देता हूँ, ये clockwise था इसलिए ऐसा, ये एंटी क्लॉकवाइज था इसलिए ये ऐसा.
So direction क्या होता है? If we assume the wrong direction, negative आ गया.
नहीं, एक assumption तो स्टार्टिंग में है. VCM ओमेगा अज्यूम करते वक्त तुम कुछ भी अज्यूम कर सकते हो. इक्वेशन कंस्ट्रक्ट करते वक्त इफ यू मेस अप देन आंसर सही नहीं आएगा. वंस यू हैव अज्यूम्ड योर डायरेक्शंस, फिर उस डायरेक्शन के हिसाब से तुम्हें सही इक्वेशन लिखना पड़ेगा. Here you can't mess up.
And if you get the negative answer, it's the opposite.
In an equation like this, you will be lucky कि चलो ज्यादा फर्क नहीं पड़ेगा. But if this equation had more terms, you would not even get the right answer. ठीक है, मैं assumption की बात कर रहा हूँ कि assume करते वक्त, variable assume करते वक्त फर्क नहीं पड़ता है. और एक बार variable assume किया है, these equations you will have to assume a sign convention and then write everything perfectly according to your assumed variables and sign convention. ठीक है?
So wherever we take the axis, the only thing that's going to depend on the axis is RCM, right? Everything else will be constant now. मतलब वो last का.
अच्छा, wherever you take the axis, yes, तू बोल रहा है ये term constant रहेगा, perfect. ये term change होगा, और बस but बाकी terms भी आ सकते हैं. You take the axis somewhere else, तो m1v का term उनका radius आ जाएगा, particle का आ जाएगा. Okay, so let's try a question out. ये approach था. Any doubt? Those who are online. Okay, great. See, done. So example करो. So let's say you had okay. So imagine you have a rod like this. Rod is moving with a velocity v. ठीक है, rod का mass m है, length l है, uniform है, ठीक है. Rod is not rotating. Okay. L/4 distance. या मे बी चलिए यहाँ पे टिप पे you have a particle of mass m. Let's keep it as m. It's moving with a velocity of 2v. Okay. And this particle strikes the tip of the rod. Okay. And the collision is inelastic. Okay. I just want you to find final omega and final VCM of the rod after collision. वही दो इक्वेशन जैसे लगाया था तुम्हें लगाना है. It's hitting the tip of the rod. Was ये center of mass है. It is on a smooth horizontal table. There's no hinge.
So omega won't be constant. In final.
होगा ना constant. वो both are m. Yeah. So just conserve linear momentum. एक पहले आफ्टर सीन ड्रॉ कर लो, assume ये variables.
वो rod का velocity opposite क्यों है?
ये तो दिया है मैंने, ऐसा दिया है, गिवन है. फाइनली कैसा होगा तुम कुछ assume करो and solve and see. डिस्कस करें, देखें. देख इसमें ना प्लीज एक चीज ध्यान दे. सो ऑल दीज क्वेश्चंस नो फर्स्ट at least try to draw the after scene so you get an idea of what variables you really need. Okay, so if this is before तो after कैसे दिखेगा एक बार draw कर लो. Now this was a perfectly inelastic collision. Okay, so the entire situation can now be just final scene can just be fully described with just two variables. All you need is a velocity at the center of the rod for and omega. ठीक है, और फर्क नहीं पड़ता है, मैं ऐसे ही राइट की तरफ गेस कर रहा हूँ and omega भी like last time ऐसे एंटी क्लॉकवाइज गेस करो, it doesn't make a difference. Okay, यार इसका वेलोसिटी तुझे एक नया वेरिएबल असाइन करने का जरूरत नहीं है, वो ओमेगा और वीसीएम के टर्म्स में आएगा. इनफैक्ट क्या होगा, लाइक वी जस्ट सॉ, उसका वेलोसिटी होगा सेंटर के साथ साथ आगे जा रहा है, फिर सेंटर के रिस्पेक्ट में रेडियस L/2 है ना, राइट? तो प्लस आर ओमेगा प्लस L/2 ओमेगा, राइट? So make sure कि अच्छा you are aware of how many unknowns are really needed. Don't keep adding unknowns. Yeah, तो VCM omega से सब कुछ describe हो जाएगा. So I have two unknowns and I need two equations. Okay, just two equations.
So VCM is you assume that, right? So what's V then?
अरे ये given है, ये दिया है. V is given to you in the question.
Yeah.
तो तेरा आंसर V के टर्म्स में होगा.
Yeah, I'm not asking that. Like
हाँ.
V is it's already moving. Yeah.
It's already moving, yes. So I just give you an example where the rod also is moving. Shoki is not going to make a big difference. ठीक है? दो equation है. First equation is conservation of linear momentum. P initial of the particle plus P initial of the rod is P final of the particle plus P final of the rod. और इस equation को लिखते वक्त always first define a direction that you're going to take as
Right side positive.
so you can take the right hand side as positive. ठीक है? ठीक है, तो right side positive लिया, लेकिन ज्यादा फर्क नहीं पड़ता है कौन सा direction तुम positive लोगे. अच्छा ले लिया right hand side as positive. Particle का initial angular momentum है right की तरफ, m into 2v है, तो positive m into 2v आ जाएगा. Okay? एंड माइनस mv. तो रॉड का अगर देखोगे तो रॉड लेफ्ट की तरफ जाना है, मास m वेलोसिटी v, तो उसका माइनस mv आ जाएगा. okay? फिर अगला वाला पार्टिकल का फाइनल
MVCM plus MVCM into L/2.
परफेक्ट. तो बेस्ड ऑन हाउ इट्स मूविंग वी टेक दिस इज VCM plus L omega by 2.
And then other
And rod के लिए वापस based on our assumption right की तरफ जा रहा है तो MVCM. ये कन्वेंशन के हिसाब से केयरफुली लिखो. सेकेंड इक्वेशन के लिए we'll apply conservation of angular momentum.
In this case, center of mass and contact don't make any.
Center of mass and
Like the choice of center.
हाँ.
This doesn't make.
हाँ, so he's saying इसमें choice of axis doesn't make a big difference. तो center of mass वाला ले सकता है या इसके line के along भी ले सकता है, कुछ भी ले सकता है. ठीक है? So which one do you want to take?
In fact, center of mass is, I think, would be easier because of calculating the angular momentum of the particle is easier than calculating the angular momentum of the rod.
ठीक है. So अगर तुझे since maybe we saw one example जहाँ पे हमने उसके बोर्ड लिया था, तो इस example में center के बोर्ड लेंगे. ठीक है? So just make sure कि whatever axis you're taking, that's an axis which is fixed. Don't make the axis also move. That will just complicate things. So I'm taking a fixed axis center of mass के line के along. उसको दो बार draw कर रहा हूँ, एक before वाले scene में और ये just after collision वाले scene में. ठीक है? So that's how it looks. Now, ठीक है? Now उस axis के about. ठीक है? So हाँ, so take a direction is very nice. Take a direction is positive. कौन सा लेना है as positive? ठीक है, तो एंटी क्लॉकवाइज को as positive ले लो. तो L initial of the particle plus L initial of the rod is L final of the particle plus L final of the rod. Okay, direction is positive, so I'm going to take anti-clockwise as positive. Particle का initial angular momentum उसके about perpendicular distance देखो कितना है, L by 2. ठीक है, so ये हो जाएगा M. अच्छा, question you'll have to ask yourself, is this anti-clockwise? If you complete this motion, anti-clockwise. ठीक है, इसको positive रखेंगे. M into 2V L by 2. Okay. The next one, L initial of the rod. दो term रहेगा इसमें, एक होगा ICM omega और एक होगा R perpendicular MVCM. Is there is there an ICM omega term?
Yes.
Initially.
Yeah.
कितना है? Initially.
Yeah, omega is 0.
Initially omega 0. तो ये term नहीं है ना? तो initially नहीं था. And R perpendicular MVCM is also 0 because there's no R perpendicular for the center of mass. तो ये वाला term भी नहीं है initially. ठीक है? Finally, तो particle का final angular momentum axis के about, right?
So MVCM plus L by 2 omega into
excuse me, sir.
हाँ.
So angular momentum of the initial particle में आपने क्या किया?
MV into R perpendicular ना, M into 2V into L by 2. इस बार हमने वो axis लिया just to change things. Okay? कुछ भी फर्क पड़ता है, तुम चाहिए तो if you want to have a fixed approach you can take that as well, फर्क नहीं पड़ेगा. तो इसमें M VCM plus L omega by 2 MVCM plus L omega by 2 into L by 2 ये पार्टिकल का फाइनल है. ठीक है, एंड रॉड का फाइनल एंगुलर मोमेंटम लिखते वक्त अगेन ओनली इट्स रोटेशन वाला आ जाएगा, ICM ओमेगा वाला टर्म आ जाएगा. एंड हमारा पहले तो ये एंटी क्लॉकवाइज था, क्या चेक करो, हाँ ये भी एंटी क्लॉकवाइज था, है ना, तो इसलिए इसको भी हमने पॉजिटिव रखा है. एंड लास्ट वाला ICM ओमेगा, वो ओमेगा भी एंटी क्लॉकवाइज है, तो ये भी पॉजिटिव रखेंगे, प्लस ml स्क्वायर बाई 12 ओमेगा. ठीक है, एंड द अदर टर्म इज एक्चुअली 0 लाइक दिस वन क्योंकि VCM is again passing through the axis.
So how did you get 3 terms in the RHS?
In the LHS
हाँ ये LHS है.
0 है ये दोनों टर्म, 0 ऐसे लिखने के लिए. ICM ओमेगा, ओमेगा 0 है, इसमें भी R परपेंडिकुलर 0, these are not there, एक ही टर्म है. Okay, so those are our two equations. इसको बस solve करना है. Just go to the next page. तो ये हो गया mv, mm कट जाएगा तो 2v minus v, ये v हो जाएगा वो 2vcm plus L omega by 2.
So, but वो वाला easier रहता है ना, other axis, because इसमें 0 हो जाता है, then RHS में 0 हो जाता है.
ठीक है, I mean that's actually good, वो axis is good, but अभी यहाँ पे भी like
अच्छा,
ये दो term 0 हो रहा है, it's fine. ठीक, you want to have a fixed approach, तेरे को ज़्यादा, you don't want to waste time making a decision, then you can stick to that axis. If the rod is not moving initially, that's like definitely the best axis. तो m वगैरह काटने के बाद 2v minus v is 2vcm plus L omega by 2. This is equation 1, right? Whatever v is equal to L omega minus vcm by 2. That's equation 1. And the other equation is
So, 1 second.
यहाँ पे m कट जाएगा. दूसरे वाले इक्वेशन में हम ये सब 0 हो रहा है. M and L can get cancelled. ये तो काट. So after cancelling M and L, we have 2v by 2 on the left hand side. We have VCM plus L omega by 2 by 2. And we have L omega by 12. So just copy that. दूसरा है 2v by 2 VCM plus L omega by 2 whole divided by 2, and we have L omega by 12. सही है? तो बस यार यहाँ से and this is चलो, in hindsight I feel that equation would have been the best. I'll tell you why. ये बात सही है कि इस इक्वेशन में दो टर्म 0 हो रहा है, 3 टर्म 0 हो रहा है, तो इस इक्वेशन में 3 ही टर्म था. एंड अगर वो वाला इक्वेशन लिखते थे तो उसमें भी 3 ही टर्म होता. बट आई स्टिल थिंक वी कांट अवॉइड दिस v. इनिशियल में भी v आएगा. सॉरी, आई रिट्रैक्ट. दोनों बोथ आर वन एंड द सेम. ऐसा
So, what did you cancel the last term?
कुछ m और l काटा सेकेंड इक्वेशन में.
No, can you go back?
0, ये दो 0 थे.
अच्छा, that's M. How did you cancel M? अच्छा, M को
m हर टर्म से कैंसिल किया
समझा.
और l हर टर्म. Now we're just solving. I mean, we have the answer. So यहाँ पे v is VCM plus L omega by 2. Okay, and v is given to us. ठीक है, v is not the unknown. तो just be clear, VCM को इधर डाल दो चाहिए तो VCM is ऊपर वाली इक्वेशन से VCM is, है ना, v minus L omega by 2 divided by 2. तो v by 2 minus L omega by 4. Okay, when you're solving, don't get exhausted and don't lose track of what is really the unknown, what is given. V is given to us. So just substitute VCM. So V, ठीक है, is v by 2 minus L omega by 4 plus L omega by 2 whole divided by 2 plus L omega by 12. Okay, तो ये v minus v by 4 is whatever, L omega by 2 minus L omega by 4 becomes L omega by 4 L omega by 8. See? So 1 by 8 plus 1 by 2.
Is the first equation.
Upper one is the first equation, green one is the second. Okay, so 2 by 24 plus 3 by 24, 5 by 24. 3v by 4 is 5 L omega by 24. तो ओमेगा आ रहा है, ये 6 हो जाएगा, तो ओमेगा आएगा 18v by 5L. यही आया था तेरा something like this.
I got 6 feet by 5. So I must have made a mistake while testing.
But I hope you guys basically got the idea. Okay, and अपना VCM भी similarly. आ जाएगा V/2 minus L omega by 4. तो V/2 minus
18 by 5 and 1.
हाँ. Yeah. So 5V/10 minus 9V/10. तो VCM मेरा आ रहा है minus 4V/10. Interesting. Okay. And minus means my direction is wrong. So I can quickly just check if this is correct. Huh? VCM minus 4V/10 आ रहा है. L omega is 18V/5. L omega by 2 is 9V/5. Okay. 18V/10 and minus 4V/10. If I go over here, (14V/10 minus 4V/10. 10V/10. सही है, मेरा आंसर सही है. You can always cross check your answer, ठीक है? अरे देते ये सही है. Just plugging it over here, I can see that final momentum is coming out to be mv. Anyways,
So one thing I'm not remembering, ये आपने अपने inelastic collision में क्या है? What does that conclude?
यार उस inelastic collision simpler case था. यहाँ पे मैंने थोड़ा ऐसे और complicate किया by giving you one more velocity over there. ठीक है? But basically inelastic collision में ये इधर stick कर रहा है. So that's why it's a slightly simpler case.
We're not going to study about elastic.
अभी देखिए ना, elastic specifically नहीं, कोई भी collision अब is case B, any random collision. ठीक है? They all have the same approach. Okay, so this is case B. Case B is not an inelastic collision. Okay, so E is not 0 in this, like we saw the last time as well. Those online कुछ भी doubt है पूछ लो. You're free to unmute as well. देखो not an inelastic collision में
We'll have 3 variables.
3 variables. You'll have 3 variables. Reason you'll have 3 variables is because after this particle, so after this particle collides with the rod, it won't stick to the rod. Because it won't stick to the rod, particle ka final velocity is not something directly related to the rod. Okay, so imagine particle ka mass is m1, rod ka mass is m2, and length is L. Particle ka ek final velocity unknown hoga, which I'm going to take as, let's say, v dash. Rod का फिर motion describe करने के लिए extended body है, सिर्फ velocity काफी नहीं है. तो rod का फिर final motion describe करने के लिए we'll need velocity of its center of mass. We'll also need omega. So there will be 3 unknowns. Okay, 3 unknowns.
What are we calculating? Velocity.
So most likely to calculate even one of them, you will need all 3 equations.
So we are calculating VCM, omega,
V dash. Any of these could be a question. So VCM and omega of the rod. And V dash of the particle. Okay.
Earlier we assumed the velocity to be VCM plus x omega, right?
Why did we assume that?
Because it was inelastic.
And it was inelastic, it was stuck to the rod. VCM plus x omega वो वाला rod का point का होगा. वो particle वो rod के साथ साथ जा रहा था, इसलिए उसका भी VCM plus x omega था. ठीक है? अच्छा, इसमें again what will be our 3 equations?
One conservation of linear momentum, conservation of angular momentum, and
E.
So E will be given, right?
E will be, of course, E will be given. Okay? Yeah. So
for the velocity of the second, like for the rod for which we consider an E, we will take VCM plus omega x, right?
yeah. Yes. Okay. So here's the 3 equations here. Like the first one is conservation of linear momentum. P initial is equal to P final. ठीक है? So just let's again, क्या दिख रहा है इसमें? साफ initial momentum. Again, always assume a direction. इस example में direction assume किया और क्या आ गया? Initial particle का m1v, rod का 0. ठीक है? Particle का finally m1v dash and rod का m2 VCM. ठीक है, रॉड का हमेशा सेंटर ऑफ मास वाला वेलोसिटीज गिव्स यू अ लीनियर मोमेंटम. तो ये इनिशियल, ये PI इक्वल टू PF हो गया. सिमिलरली यू कैन अगेन चूज एन एक्सिस एंड अप्लाई LI इक्वल टू LF अबाउट दैट एक्सिस. ओके, सो लेट्स जस्ट, आई एम कॉलिंग माय एक्सिस A and I'm going to again use that one. Same thing, I think you have either available as a choice. If you want a fixed approach, maybe you can go for this. Okay. अच्छा, इसके कारण इनिशियल एंगुलर मोमेंटम पार्टिकल का 0, रॉड का तो है ही 0. रॉड का दोनों टर्म ICM ओमेगा प्लस RCM क्रॉस MVCM दोनों टर्म 0 है. ठीक है. पार्टिकल का फाइनल एंगुलर मोमेंटम अगेन 0 है. रॉड का फाइनल एंगुलर मोमेंटम, अच्छा ये सब लिखते वक्त फिक्स अ डायरेक्शन. लेट्स से वी टेक एंटी क्लॉकवाइज पॉजिटिव लाइक लास्ट टाइम. वैसे ही रॉड का ICM ओमेगा एंटी क्लॉकवाइज, सो दैट टर्म विल बी पॉजिटिव. ओमेगा minus MVCM x. Okay, so this time the perpendicular distance is again it's going to be x. So minus, because ये clockwise sense में है, तो minus MVCM perpendicular distance. This was clockwise, hence the minus sign. This guy was anti-clockwise. Okay. Now RHS, पार्टिकल का 0, रॉड का ICM ओमेगा, है ना, ये ऐसा घूम रहा है एंटी क्लॉकवाइज सेंस में. एंटी क्लॉकवाइज पॉजिटिव लिया तो ICM ml²/12 ओमेगा. एंड रॉड का एक RCM क्रॉस MVCM टर्म होता है ना, है ना, तो उसको VCM को आगे पीछे एक्सटेंड करके देखो, परपेंडिकुलर डिस्टेंस x आ रहा है एक्सिस से, right? So MVCM into x is the last term.
Actually, we're not taking axis on center of mass here.
वो भी ले सकता था, इस केस में इधर ही लिया है, वो भी ले सकता था. वो सेंटर ऑफ मास का लेगा तो M1Vx आएगा, इनिशियल रॉड का 0, फाइनल M1V' x आएगा, राइट, RHS में. रॉड का ICM ओमेगा आएगा, VCM वाला टर्म नहीं आएगा. This definitely looks better over here because directly get a relation between omega and VCM. All right, these were the two equations. The third one is
Would be from
E wala, and
VCM plus omega x minus v dash is equal to E times
Makes sense. V.
yes,
V separation is equal to E times v over.
yes. तो क्या V separation by V approach is E. ठीक है. अब इसमें as I mentioned last time as well, these involve velocities, relative velocities of the points of contact. ठीक है. Be very clear. ऊपर वाला equation, first equation देखो. Thank you. First equation is always thanks. First equation is always the linear momentum equation is always going to involve center of mass wale velocities. Okay, linear momentum is velocity of the center of mass, but this equation is always for points of contact. Be very crystal clear about those concepts. So V separation likhte waqt you need point of contact ka velocity, so you'd want to find this, which will be VCM plus x omega, as we just saw, right? Inelastic के वक्त we understood how to write this. ये वाला point VCM plus x omega के साथ आगे जा रहा है, ये अलग velocity के साथ आ रहा है. ठीक. अच्छा, और ये भी assumption है. I did not waste time thinking ये particle पीछे आएगा आगे जाएगा. मैंने assume किया है, but वो assume करने के बाद you have to plug in these terms properly. Okay. So now because I assumed right, this term is going to be a positive m1 v dash, and velocity of separation likhte waqt bhi I'm going to take the difference because they are like two particles moving in the same direction. So relative velocity is the difference of the two. Faster minus slower. आगे वाला faster होगा collision के बाद. तो आगे वाला velocity minus पीछे वाला velocity. तो पीछे वाला velocity is v dash. ये हो गया अपना relative velocity after collision. Initial relative velocity before collision, this is 0. It's going to be V. Let me know if you didn't get anything. Yeah? So those will be your three equations. Okay. My voice is cracking at 5. It just started cracking. Is it still cracking? Yes. Okay, it's not cracking. ठीक है, चलो एक क्वेश्चन कर लो.
So the which one is faster?
Which?
So VCM plus x omega is faster. That's what you said.
ये इक्वेशन कैसे लिखा, ये पूछ रहा है तो.
हाँ, वो तो समझ गया
relative velocity. हाँ. So, हाँ.
How did you conclude which one is faster?
नहीं, so when two objects collide,
yeah,
after collision they should be separating.
Yeah.
If they're going in the same direction, जो आगे है, that guy should be faster, no? तभी they'll be separating. Otherwise, they'll still be approaching each other. Two cars are, है ना, एक गाड़ी आगे, एक गाड़ी पीछे है. If they're separating, the car ahead should be faster.
Or constant velocity will be where like they're moving at the same speed, but this guy still is okay as compared to this one.
हाँ, agreed. But if they are separating after collision, they have to separate. If they are separating, आगे वाला faster होगा. ये भी मतलब सही से लिखना. These two terms that you write, they have to be positive. It has to be technically relative speed after collision, relative speed before collision. They have to be positive terms. E has to be positive. Okay. So if you write V dash minus VCM plus x omega, again, it'll get messed up.
This case is like the most difficult one.
हाँ, you'll have three equations.
But that will कैसे भी लेके like that's fine, right? Because direction तो last में पता चलेगा. अगर we took the wrong direction, then negative आ जाएगा.
वो ठीक है, मैं बस इतना बोल रहा हूँ. तू एक बार डायरेक्शन अज्यूम किया ना, तो फिर तुझे ये दो इक्वेशन सही से लिखना पड़ेगा based on that assumption. जैसे इसमें if you write v dash minus vcm plus x omega, there's no coming back from that. गलत ही हो जाएगा. So these you think carefully and write. My habit is always to just take keep everything towards the right. ज्यादा उल्टा उल्टा सोचना नहीं पड़ता.
तो मतलब इसका this will depend कि अगर हम लोग clockwise ले रहे हैं कि anti clockwise.
कौन सा?
ये जो आपने v separation लिखा.
हाँ.
अगर
हाँ, अगर नहीं क्लॉकवाइज एंटी क्लॉकवाइज का नहीं, बट अगर मैं v डैश को लेफ्ट की तरफ लेता था, so then this would have been a plus over here and this would have been minus m1 v dash. Sometimes ठीक है, the question could be like this, but maybe चलो मान लो मेंस एग्जाम है, they may not really ask you to use all three equations. हो सकता है they may just they may give you omega and they may just ask you VCM. Either way, you need to be familiar with these equations.
And if the rod was moving with another velocity, then वो denominator में v minus
v नहीं, rod is moving with another velocity, तो फिर तेरे को इसका वेलोसिटी निकालना पड़ेगा. रॉड से मूव करे तो इसका भी वेलोसिटी v होगा. तो रिलेटिव वेलोसिटी v बेस्ड ऑन हाउ इट्स मूविंग ना, v एंड उसका रिलेटिव वेलोसिटी आता है. जैसा पिछला केस वाला अगर होता, then the denominator would be v plus v. ये पार्टिकल v वेलोसिटी से आ रहा है, वो भी v से आ रहा है. Make sure whatever you're seeing is always the velocity. In fact, that's why I would say label these. Label the velocities of the points of contact. Okay?
That's a question we'll see.
हाँ, but let's ठीक है, इसमें let's not go overboard. वो rod को let's not make it move. I think in itself ये अच्छा question है. It could move as well, but it's हाँ, and it's like ठीक है, it's just you've understood the concept. वो थोड़ा ऐसा ही घोड़ागिरी जैसा होगा. So let's just say कि ये पार्टिकल है, पार्टिकल से मतलब रॉड के सेंटर वाले लाइन से L/4 डिस्टेंस नीचे, L/4 डिस्टेंस नीचे, the particle strikes the rod. Okay. So after collision, find the omega of the rod.
Is the mass of the particle at the rod?
Yeah, mn.
So can they give questions like this where वो particle is not a point mass, like वो भी एक rigid body and वो भी एक rigid body, and the rigid body is second another rigid body.
But that would be very deep.
नहीं, but we can just like replace ICM से, मतलब वो the whole मतलब we can just replace whatever shape of the object is.
They could, as long as it's a good question, where your concepts are tested and not just ऐसे calculations 10 पेज का, वो टेस्ट नहीं करना.
So for finding omega, we have to use all three equations because
think so. I would say that's actually a good question. You should think ideally, even if you don't write out equations like what all would omega involve.
What's E?
E देता हूँ. Sorry, E को half ले लो. Okay? Sorry, thanks. Given E equal to 1/2. Looking at this, I think you'll have to use all. ओमेगा के लिए VCM चाहिए, बट VCM के लिए कोई भी इक्वेशन उठाओ V भी चाहिए, तो you'll have to V नहीं V dash चाहिए, you'll have to use all. कभी हो सकता है ऐसा क्वेश्चन आए वेयर ओमेगा और VCM का एक इक्वेशन था ना, तो they could have given you just VCM and people by choosing this right axis and the right equation they can solve it in one line, one equation. ये भी हो सकता है सवाल.
They'll give all these values and VCM.
हाँ, ऐसा भी अच्छा सवाल बन सकता है. Like
And there will be two variables.
नहीं, ये सारी values दिया और VCM भी दे दिया, even though they don't need to give. Their intent is to make the equation apply करके आंसर निकाल दो. Just understand.
We'll have two equations, right?
एक इक्वेशन अगर VCM दिया तो एक इक्वेशन ना, ओमेगा और VCM का एक डायरेक्ट रिश्ता है. If I conserve angular momentum about this axis, so sometimes they can do stuff like that. Somebody else 2-3 equation लिख के आंसर निकाल रहा है. Some smart kid identify करके. Always think 1 or 2 steps ahead. What the unknowns are, what equations you need.
So angular momentum, why don't we use V dash?
तू बता क्या एक्सेस लिया था हमने.
अच्छा 0 हो गया.
हाँ, वो उसका नहीं आया. Done?
Yes, sir.
I would say हमेशा वो steps करना, like at least after वाला image बनाया
हाँ,
है ना, तो
हो गया मतलब आपका task.
अच्छा ठीक है. So just like the minute this is given to you, quickly make the after image, assume your variables. तेरे को अगर आ रहा है तो you can continue. इसमें ये सब किया, VCM, ओमेगा, L/4 डिस्टेंस नीचे, इसका वेलोसिटी V डैश, फिर यही पे since you know you'll be applying quotient of restitution equation, might as well label point of contact का velocity. तो इसका velocity 0, इसका collision के बाद center के साथ साथ VCM, but center के respect में आगे की तरफ R ओमेगा, इसके लिए center से distance है L/4. Right? Okay. First equation. तो orally बोल दे पहला वाला.
V is equal to V naught plus VCM. मतलब ये करके.
हाँ बोल वापस बोल.
Like the final result. V is equal to V dash plus VCM. अच्छा चला.
हाँ mv plus 0, you're right, is equal to mv dash plus mvcm. Perfect. तो ये एक इक्वेशन हो गया इजी वाला. दूसरा है कंजर्वेशन ऑफ एंगुलर मोमेंटम अबाउट, अगेन दैट्स अ गुड एक्सिस. ठीक है, तो ये वाला इधर एक एक्सिस लेते हैं ए, ये लाइन में एक्सिस ए. ओके, सो दिस इज L about A, Li equal to LF about A. Angular momentum of the particle both times, पहले भी 0, बाद में भी 0 आएगा. नाइस, सही है. ठीक है, तो पार्टिकल का 0, रॉड का 0, बाद में भी पार्टिकल का 0, रॉड का 2 है. परफेक्ट. ml²/12 ओमेगा, डायरेक्शन हम एंटी क्लॉकवाइज. डायरेक्शन ml²/12 ओमेगा. ml²/12 omega minus r perpendicular MVCM. Okay, what about the last one?
1/2.
1/2.
1/2 is equal to VCM plus L/4 minus V dash 5V.
Perfect. Relative velocity बाद में
VCM plus L/4 omega
minus V dash. That's it. Yeah, nice. And then once you have all these equations you're staring at, just try to keep in mind like what you know. V is known. ठीक है, V is known. Omega तो तुम्हें चाहिए. So here we have a nice relation between omega and VCM. यहाँ पे क्या है VCM and V dash. Okay. यहाँ पे V dash.
Replace omega.
Yeah.
And instead of V, we could do V dash plus VC. And we get the direct.
Can you repeat that? क्या बोल रहा है तू?
We'll substitute the value of omega by the second equation.
हाँ. Where?
In the third equation.
In the third equation. Okay.
And substitute the value of V from the first equation. And then we'll only get two variables and we'll get the relation.
Substitute the value of V.
Yeah.
So that's the thing. V is a known.
We could get the relation of V dash and VCM. So, and then substitute
How?
that relation.
Okay.
Two variables, right? So, and use that relation in the first equation.
Well, we can do anything.
Yeah, we can do it.
हाँ ठीक है परफेक्ट तो यार सही है तो यहाँ से चलो जल्दी देखते हैं एक बार आंसर क्या है तो इधर छोटे में लिख लेता हूँ सो ओमेगा फ्रॉम द फर्स्ट इक्वेशन gives me if I cancel second equation if I cancel m and I cancel l and I cancel 3 l omega is 3 VCM very nice ठीक है फिर
So can we generalize these results so that we can remember it?
कुछ नहीं there can be hundreds of different cases remember the concepts यहाँ पे like collision का याद करना है two particle collision then that's fine but उसमें भी they can play around with so many things and it's you don't need to remember the results and sometimes remembering results most of the times will not even be enough I would say practice ऐसे questions करो concepts करो that'll be a lot better ठीक है तो L omega 3 VCM यहाँ पे मैं डाल देता हूँ तो in fact वहां से एक बार वो V dash क्या है V dash is V minus VCM right so I would maybe put everything over here okay perfect V dash is V minus VCM which also makes it V minus L omega by 3 so let's put everything over here so half या अगर V को left hand side पे लाएंगे तो V by 2 is equal to VCM is L omega by 3 ठीक है बस solve करो you can have your own way plus L omega by 4 minus V dash is V minus VCM V minus L omega by 3 okay तो यहाँ पे आ जाएगा V by 2 is L omega
Omega would come as 8V by 11.
okay
18V by 11.
okay so L omega by 3 plus L omega by 4 plus L omega by 3 और ये minus V उधर जाएगा 3V by 2 is L omega by 4 plus 4 8 plus 3 11 by 12 right? Cool ठीक है good
So I was wondering, can we
हाँ.
solve these questions using working with equivalence?
18V by 11 ना ठीक तो बोल क्या कर सकते हैं उससे नहीं first and foremost work energy theorem is not even
Yeah, because there's no external force.
when the collision is not elastic there is going to be some either heat released or some potential energy because of deformation stored in the body which you don't know and you can't write you can't even apply conservation of energy in those cases because you don't know kitna heat release ho raha hai and agar elastic bhi hai tabhi bhi if you remember I said conservation of energy is one equation wo bhi
It will have a square term.
it'll have a V square term in it and
And it will get the same result as E.
it'll give you the same result as E equal to 1 V separation as V approach if you club it with momentum conservation वो ये result देगा तो why even waste time वो गंदा सा equation है और एक equation है ऐसा जादू से मतलब तीन unknown तीन ही equation से आएगा there's no other way ठीक है Okay, cool. So that settles angular collisions. Angular impulse. Heading down. Angular impulse. In fact, even as we see that, maybe I'll just heading डाल सकते हो चाहिए तो angular impulse, but I'll contrast it with linear impulse. You'll see how they are related to each other and how they are in a way similar. And actually इसमें linear impulse का जो symbol होता है, that's typically J. Even online if you search, but your booklet has also mentioned angular impulse का symbol as J. Online बहुत ढूंढा, that doesn't seem to be a good symbol assigned for this term. So what we'll do is let's use linear impulse के लिए JL, just to make a small differentiation between them. Rather JL nahi, let's use JP, because this deals with linear momentum, as you'll see. And angular impulse के लिए let's just use
linear impulse is change in force, right?
is change in linear momentum, and this guy is going to be change in angular momentum. तो इसलिए JP JL, ठीक है? अच्छा, how are they defined? So firstly, linear impulse. ऐसा difference नहीं दे रहा हूँ, I'm just dividing the page into two. So linear impulse was defined for a force, ठीक है? So it was defined as integration of that force over the time during which that force was acting, ठीक है? And in case of collision, yes, that's the normal force. And addition of all these linear impulses, ठीक है, technically एक ही होगा, but if there were multiple, then the addition of all of them gives you the change in linear momentum, ठीक है? So सारे linear impulses एक साथ मिलके will give you change in linear momentum. Typically एक होता है, but I'm just writing it this way क्योंकि कभी ऐसा हो सकता है कि एक rod था, hinged था, तुमने ऐसा एक linear impulse दिया जिसके कारण hinge ने एक hinge as a reaction to that उसने एक अलग linear impulse दिया. तब मैं नहीं बोल सकता हूँ कि मैंने जो impulse दिया that is change in linear momentum. मैंने जो दिया, hinge ने जो दिया, उनका combination gives you change in linear momentum. So technically addition of all the linear impulses at a given point gives you the change in linear momentum. Okay. And change in linear momentum is basically change in MVCM. And more often than not, if your M is not changing, then you can basically use this to find how velocity of the center of mass changes. तो linear impulse से center of mass का velocity कैसा change हो रहा है वो तुम्हें मिलेगा. Okay. Angular impulse के लिए it's defined as integration of torque dt. Okay. Oops, sorry. भी force है, ठीक है? Defined as integral torque dt t initial से लेकर t final. Okay. Summation of all these angular impulses, and this is about an axis. Yes, so angular impulse is always defined about an axis, and it is nothing but the integration of torque about that axis with respect to time का integration. ठीक है? तो जैसा force से linear impulse आता है वैसे torque से angular impulse आता है. Angular impulse basically is the change in angular momentum caused. Typically एक होगा. So angular impulse is the change in angular momentum caused by that angular impulse. Multiple है तो सभी को add करके you get net change in angular impulse. But typically एक होगा. तो sigma summation JL gives you total change in angular momentum. इसमें I would suggest you can use ठीक है। अब जैसे यहाँ पे लेफ्ट हैंड साइड में वी यूज्ड लीनियर इम्पल्स टू फाइंड चेंज इन VCM. Similarly, we would want to use that to find change in omega. Right? We want to use that to find change in omega.
But moment of inertia should be constant.
Ha. Moment of inertia would be constant, but how do I say this? So a good, so how does L relate to omega? So over here, it's nice to pick a good axis. So like we know those two special case results. Okay, one was L about the center of mass is ICM omega, right? So you could use that. You could use the center of mass as your axis. Okay, you could use the center of mass as your axis, which will give you total angular impulse about the center of mass is change in angular momentum about the center of mass. Change in angular momentum of the center of mass can be written as change in ICM omega. And ICM wouldn't change. छोटा टाइम इंटरवल की बात कर रहे हैं, बॉडी डिफॉर्म वगैरह नहीं हुआ है, तो ICM तो कांस्टेंट रहेगा. सो और ये डेल्टा ओमेगा यहां से मिलेगा. ठीक. सो और यू कुड टेक I about the IOR. Okay, so these are two options you can use while trying to figure out कि ऐसा कोई इम्पल्स के कारण तो बॉडी का एंगुलर मोमेंटम एंगुलर वेलोसिटी एंड सेंटर ऑफ मास का वेलोसिटी कैसे चेंज होता है. ठीक है. हम देखेंगे कि लीनियर इम्पल्स के कारण एंगुलर इम्पल्स कितना आता है. we'll see that as well. Okay,
So why do we only write ICM?
L about the center of mass is ICM omega. L about the instantaneous axis of rotation is I about the instantaneous axis of rotation omega. And you would not want to sit on any other axis of the body, because if you sit on some other axis, no, center of mass ka motion is nice, but any other axis would have a very complicated motion. So you'll have to think about torque, especially torque equal to 0 बोलते वक्त you'll have to think कि यार ये axis घूम रहा है, आगे जा रहा है, उसका acceleration क्या होगा, becomes messy. So I'm repeatedly just writing this so that you guys apply angular momentum conservation and find angular momentum also about either center mass or IOR or about a point on the road. यहाँ पे I'm avoiding a simple point fixed axis just because इनका फॉर्मूला इजी है. डेल्टा एल इनके अबाउट निकालेंगे, so it's a very simple relation between delta L and omega. Okay, anyway, so this is delta L about the IOR, which ultimately becomes I about IOR into delta omega. So you can use either of the two, and थोड़े examples में तुम्हें समझ में आएगा why you would use which, when you would use what. ठीक है, हो गया. लिख ले ये सब. अच्छा, you can also find the angular impulse due to an impulse. Okay, so angular impulse due to a linear impulse.
It would be linear impulse cross R.
Perfect. उल्टा तो मतलब R cross linear impulse. जैसा torque is R cross F, वैसा ही angular impulse is R cross linear impulse. So if you go back to that, JL is integral tau dt, T initial, so T final. Torque is R cross F. R is collision के वक्त वो जो छोटा सा फोर्स हम कंसिडर कर रहे हैं वो मतलब वो फोर्स का पोजीशन जहाँ पे अप्लाई किया है, दैट्स नॉट गोइंग टू चेंज मच, यू नो, स्प्लिट सेकंड्स के लिए हम ये इंपल्स लगाते हैं. सो r इज टेक्निकली गोइंग टू बी अ कांस्टेंट, तो r बाहर चला जाएगा. दिस इज गोइंग टू बिकम इंटीग्रल फोर्स dt. Integral force dt is going to become this thing, jp. So that shows ki you find an angular impulse just like you find you find an angular impulse due to a linear impulse, the same way you find torque due to a force.
So if there are more than, like if there are multiple forces, we have to individually add them.
हाँ, if there are
would vary.
if there are multiple forces, तुम हर force के corresponding torque निकाल के बाद में add करोगे. वैसे ही if there are multiple linear impulses, हर linear impulse के कारण angular impulse निकाल के add करोगे.
So like it's not necessary, right? कि अगर linear impulse होगा तो there would be an angular impulse, because if the force is on the center of mass, so like it cannot be zero. अच्छा हाँ.
हाँ, if the force, just like if a force passes through your axis, torque is zero. वैसे if your angular impulse passes through an axis, if your linear impulse passes through an axis, angular impulse about that axis is zero. Okay. Basically, इसमें you can use angular impulse. Practically तो ये use करेंगे. Angular impulse is r perpendicular into linear impulse. Just like torque is r perpendicular into F. Okay. Okay. All right. Same as finding torque due to a force. I think you've seen enough based on the examples I've taken. So, yes, maybe we say type 1 is a hinged rod. Okay. But I would suggest कि तुम try कर लो an example. Okay. So let's say यहाँ पे एक rod है, rod का mass m है, length l है, ठीक है, और मैंने इसको एक यहाँ से x distance नीचे एक linear impulse दे दिया. Okay. X distance नीचे I've given it a linear impulse. Linear impulse is A. Okay, इतना A amount का linear impulse दे दिया. So I want you to find the final omega of the rod.
So अगर linear impulse दिया तो then the angular impulse will be constant, right? Like वो zero से final में होगा, right?
क्या?
Angular impulse will be constant, right?
Constant मतलब तुम एंगुलर इम्पल्स एक लीनियर इम्पल्स के कारण कोई भी एक्सिस के अबाउट ले सकते हो. ये अब यू विल थिंक इन दिस क्वेश्चन व्हाट यू वुड वांट टू डू.
X is a constant, right?
X is a constant. हाँ.
I got it.
J is equal to X A. Then
सही बोला तूने. फिर
we can apply the previous concept. Yeah.
so how would you find omega?
ICM into like the angular momentum would be ICM into.
So you're saying कि we should use this one. Are you saying that? Angular impulse about center of mass is ICM omega. That's fine. But notice कि मैंने यहाँ पे summation लिखा है. तो क्या problem है? क्या problem हो सकता है?
There would be a reaction forced by the hinge.
Yes. इसमें hinge चुप नहीं बैठेगा. Hinge के कारण एक reaction आने वाला है. So if I try to find omega by finding angular impulse about the hinge, by using angular impulse about center masses ICM delta omega, this is not the only angular impulse about the center mass. Hinge भी angular impulse लगाएगा.
So we need to find the impulse, the linear impulse due to.
अच्छा, yeah. So we'll just subtract the hinge का.
But hinge का पता ही नहीं ना क्या है force. So then what becomes the next choice? You have just 3 equations.
तो hinge का पता नहीं लगा सकते.
तू बता यार कैसे पता लगाएंगे? पहले तो ये सवाल का आंसर निकाल, then think about other things ना.
We can use that one now. Say that.
So we can know ICM of hinge.
No below.
अच्छा ये देख, ये तू ये अब ये सजेस्ट कर रहा है.
No below.
ये हाँ, this is the way of finding angular impulse due to a linear impulse.
Yeah.
So this is just तेरे को जो axis के about angular impulse चाहिए तो अब निकाल सकते हैं.
Yeah, so we know ICM, right? And we can like assume a variable W. Sorry, omega.
Are you talking about this equation?
Yeah.
So I'm saying कि this is summation of all angular impulse about the center of mass equal to ICM delta omega. इसमें hinge का भी angular impulse आएगा center of mass के about. वो term हमें नहीं पता. यहाँ पे भी क्या problem है?
Like we know n delta VCM would be 0 because VCM would be 0.
Why will VCM be 0 afterwards?
It's
तो घूमेगा ना. If I hit the rod, it will rotate.
but not at the center of mass.
But VCM रहेगा ना. Hinge.
Yeah.
So this also cannot be used because इसमें भी summation JP में hinge का impulse आएगा.
You can find VCM in terms of omega.
Yeah, R omega. No, X omega.
Agreed. सवाल है find omega. Omega is not known. VCM is also not known. दोनों related हैं. But ये equation से आंसर नहीं आएगा. क्यों? Hinge का impulse है. ये equation से भी आंसर नहीं आएगा. क्यों? Hinge का impulse है. इससे आएगा क्या?
Yes.
क्योंकि hinge का angular impulse about the hinge itself will be 0. If you take the hinge as the axis,
I did that only.
हाँ.
Right. That's why I was wondering what.
If you take the hinge as the axis, उसके about
The torque would be 0.
torque 0 होगा.
Hinge में कहाँ पे axis?
Hinge को ही axis
Hinge को ही axis.
hinge को axis लोगे ना, hinge के about तो JL लिखने की कोशिश करेगा, वो JL फिर सिर्फ इसका आएगा, hinge वाले force का नहीं आएगा.
No sir, hinge के कौन से points पे?
hinge एक point. ठीक है. तो यहाँ पे क्या है ना, ये hinge का impulse कुछ आ जाएगा. Okay.
That would be 0.
And if I take that itself as the axis, उसके about angular impulse 0 आएगा.
ICM तो ml square by.
That will be I about that axis omega.
ml square by 3.
हाँ, ml square by 3 होगा.
I did that only, but
अच्छा तू बोला कुछ और. Cool, fine. कर लो. ठीक है. तो you guys saw, no? I'll just write out the reasoning and all. अब आंसर क्या आएगा?
Omega finally would be 3x upon ml. Omega initial is 0, right?
Did I give you homework last time?
Yes, sir.
दिया था क्या? Just I would say add to that. ये बता देता हूँ, but add to that exercise 1, 79 to 86. You have again some nice questions on conservation of angular momentum. So just quickly wrap this up because to rush to the other, but angular impulse above the IOR is going to be, so angular impulse.
So 79 के पहले all the questions. ये भी होगा.
79 के सब नहीं दिया है ना?
सब नहीं दिया.
मैंने हाँ उसमें कुछ रोलिंग के क्वेश्चंस हैं. Just but this is like specifically angular impulse, angular momentum, so just try that.
So AX is equal to ml square by 3.
Yes, perfect. Okay. So is equal to ml square by 3 omega final minus initial, which is 0. Okay. ये anti-clockwise है, ये है ही नहीं, and this one is again x into a. That's it.
mx square.
That's also anti-clockwise. ml square by 3. क्यों x square? ये rod का angular momentum है. That doesn't rod का momentum inertia has nothing to do with where I'm hitting the rod ना. वो तो ml square by 3 ही होगा. ठीक है? That's it. So this is the answer. Perfect.
So for these types of questions, we can by default take IAOR.
Yes.
Then,
If there's a hinge, yes. Okay.
because like IAOR and ICM would intersect usually, and if it's not the case, then we already take IAOR.
So you'll see कि for this it's good to take the IOR. ठीक है? And
Like when ICM is taken,
हाँ.
then CM and IOR would intersect, and they would be at the same point, right? Like when we take ICM, then CM and IOR would intersect, right?
क्यों?
Okay, that's not necessary.
Not necessary. Huh? So homework में just in the previous question, I would first एक तो these we'll discuss in class itself. So just by me. So in the previous question, find the impulse by the hinge. Find the impulse by the hinge. Okay. Find x so that the impulse by the hinge is 0. And एक और क्वेश्चन देता हूँ. तो एक और टाइप 2 वाला क्वेश्चन. टाइप 2 is a free rod without a hinge. Okay. So again, you guys try this at home, and I'll just explain that in the next class. Most probably you'll get it. So this guy, अब इसमें hinge ही नहीं है, and
There would be no non-force and no impulse by the hand.
yes,
So it was the homework.
यही लिख रहा हूँ. GP equal to A. एक linear impulse डाल रहा हूँ, ठीक है, at the edge of the rod, and rod का mass m है, length L है. In this question, you'll find VCM and you'll find omega
So to
of the rod.
change in angular momentum is of वो rod का. Like when we talk about angular impulse, we're talking about rod का angular impulse, like.
हाँ, angular momentum of the rod. हाँ, angular impulse was given to the rod. Okay, again, find the impulse by the hinge in the previous question. Find x so that the impulse by the hinge is 0.
So we'll use the first formula and like already know the result.
So in the question you gave, are we assuming the initial angular momentum of the rod to be 0?
हाँ, the rod is not moving. Initial 0. हाँ, the rod is at rest. Yes.
And इसके चलते फिर उसको एक ओमेगा मिलता है, the particle the angular momentum change. Can you read the homework?
हाँ, I'll just share this. एक सेकंड ना. If you want, you can just take a maybe photo of this, so you get all the notes.
Google, yeah.
Class हो गया?
हाँ, हो गया. Again, doubts, homework doubts, just ask for the group. Yeah, come a little.
I think I have all sessions, right? Because we got time.
I have, yeah. वो भी